Well, good morning, everyone. Welcome back. Today, in this lecture, I want to talk about strategic interaction in changing environments. So if you think about macroeconomics in a nutshell, it's really individual optimization and market clearing. And as I think I also mentioned yesterday, the dominant paradigm remains the full information rational expectations equilibrium. Yesterday, we thought a bit about relaxing the full information assumption, and today we're going to think a bit about relaxing the rational expectations assumption. And yesterday, we saw how if you introduce the possibility of costly information in a changing environment, then you can get noisy and frequent adjustment. And importantly, this costly information can generate deviations, systematic deviations from full information outcomes that don't just wash out with aggregation. And that can have implications for aggregate outcomes that are quantitatively quite large. So I showed you at the end of yesterday's lecture how estimates of how costly information is, at least when it comes to US data on price setting, have been, are pretty significant. And their implications for how flexibly the economy responds to shocks is also quantitatively pretty significant. Okay? What I didn't talk about at all yesterday is one of the reasons why these costly information frictions actually have such big systematic effects that don't wash out with aggregation is because of the fact that in macro decision making is done in a strategic context where often your payoff depends on your action relative to the actions of others. Okay, so that's what I'm going to talk about today, and I'm going to kind of continue thinking about these issues in the context of a price setting problem. Okay, so the plan is I want to talk a bit about higher order beliefs and the role that strategic complementarities play in shaping aggregate dynamics. Then I'm going to talk about bounded rationality and strategic sophistication and level K models. And I'm going to show you an experiment where we try to test level K in a setting that tries to mimic kind of the key features that we think are important for defining decision making in a macro context. That is, you make many decisions over time, and the environment changes slowly. There's some underlying slow change in the environment. And of course, your payoffs depend on what you're doing relative to what others are doing. Okay? Okay, so let's start with higher order beliefs. So many individual payoffs in many contexts depend on the actions of others, not just on some exogenous fundamental that you can track like we were doing yesterday. So for example, I can set up the static price setting problem just like I did yesterday, so the same kind of problem where the optimal price depends on the firm's own idiosyncratic market conditions and then the state of the aggregate economy. You can express that in this nice compact form, saying that the optimal price that this firm is going to set in a static context, let's forget about menu costs and dynamics. So just think about a firm setting its price period by period. It's going to be a linear combination of its belief about the fundamental. I'm going to call that Z. That's some exogenous thing. And its belief about the aggregate price or the average price set by other firms in the market. I'm going to call that P bar. And how does PI depend on P bar? Well, it depends with this constant alpha that in this price setting problem is going to be a function of things like preferences, like consumer preferences, things like the production technology of the firm, and things like market structure, how segmented are the markets that it's operating in, how competitive they are, stuff like that, right? So alpha in macro is going to be an endogenous object. And typically, we think that actually alpha is not 0, and in macro, we think that alpha is a number between 0 and 1. In that actions are strategic complements. If other firms are setting high prices, my optimal price is going to tend to be high. If other firms are setting low prices, my optimal price is going to tend to be low. In finance settings, more commonly alpha is going to be negative. Actions are going to be strategic substitutes. If everybody's buying a house or buying Bitcoin, maybe now is not the best time for me to buy a house or to buy Bitcoin. Right? So I'm going to focus on the case of strategic complementarity. And in order for macro models to get the kind of dynamics that we see in macro data, we're often going to need an alpha that is quite high. We're going to need a strong degree of strategic complementarities. We're going to need firms to really care a lot about what other firms are doing. So we want to understand how do they think about how other firms are doing. And to do that, we're going to start with the rational expectations benchmark and then try to see can we deviate from that in some sensible, disciplined way. Okay, so first, if the environment is the same for everybody, and if information sets are homogeneous, and everybody knows this to be the case, then you can infer the actions of others just purely by introspection. So given the law of motion for the optimal price that I showed you before, full information rational expectations just solves the fixed point problem. Everybody sets a price that is equal to the fundamental over 1 minus alpha, where alpha, again, is the degree of strategic complementarity.
Could you just explain what you mean by information sets being homogeneous? It means that they look the same modulo the particular firm's identity?
They have.
To all firms?
So think of it as all the information that one agent has, all agents have. So like there's public.
They have their own information at their own firm, which presumably.
And that's common knowledge in this case.
Oh.
So actually in this case it's full information. Everybody knows everything perfectly.
Okay.
You could put an expectations operator here as long as we all know, even if we know little, as long as we all know exactly the same little thing and we know that we know the same little thing,
Okay.
then I can infer what you're going to do just based on thinking about what I would like to do because the equilibrium is going to be symmetric. Okay, so this is easy. There's another easy case. You might have a situation more plausibly where information sets are dispersed. I have some private information about my own market conditions, or I just have private information. I have a noisy signal about the aggregate state as well, right? So information is dispersed, but if actions are independent, if alpha is 0, then I don't really care about what you're doing, and so I'm just going to forecast the fundamental and set my price based on my own individual expectations, and then the average price is going to adjust just as according to the average expectation in the economy. So, and this is actually not going to amount to much in the aggregate, right? If signals are unbiased, a lot of the mistakes that you make in your own idiosyncratic signal or that I make is going to wash out with aggregation, right? So just because we have dispersed information doesn't mean that it's actually going to have any real bite for aggregate outcomes, right? That it's going to lead to any meaningful deviation from the full information rational expectations outcomes. Just like, by the way, just the mere presence of adjustment costs doesn't guarantee that these frictions actually matter for aggregate outcomes, right? So what we, where things change significantly and get interesting is if beliefs are dispersed and actions are strategic complements or substitutes. Here I'm going to focus on the strategic complements case. Okay, so if beliefs are dispersed, the decision maker no longer knows with certainty what others know and what others will do. And this time the decision maker actually cares about that. This time it matters, right? So each decision maker is going to try to form expectations about the actions of others, right? But the actions of others reflect their own expectations about the actions of others, right? So the decision maker I must now form expectations about the expectations of others about the actions of others. But these expectations that other people have about the actions that people do, in turn depend on the expectations that they have about the expectations that other people have about what other people do. Right? I spent a lot of time on these sentences. And so you keep going, right? You keep forming these iterated expectations, and but it's okay because rational expectations is here, and so. In rational expectations, first order and higher order beliefs are pinned down by the model, right? So if we assume that decision makers know the structure of the economy, so they know that law of motion, and they know the shocks, then the decision makers, the shock processes, then a decision maker's first order expectation is just the mathematical expectation of the variable in question, in this case, let's say ZT, the fundamental, conditioning on that agent's information set, right? So we can compute that. And then if, in addition, we assume that decision makers have common knowledge of rationality, right? Then the second order expectation, so DMI's belief about the average action of people, is going to also be the mathematical expectation of other people's actions and hence of other people's beliefs, conditional on I's information set. Okay? And we can iterate this, continuing with higher order knowledge of rationality, and you can solve out the full set of higher order beliefs until you reach level infinity. So you can iterate the pricing equation, and you say that the aggregate price level in an economy is going to be a weighted average of the higher order average expectations of the fundamental, right? This Z is an exogenous variable. These are going to be higher order beliefs about this fundamental, right? Where the weights that I put on each higher order belief depend on the degree of strategic complementarity in the economy. That's it, right? On alpha. Okay. Note that the weights that I put on higher order beliefs are increasing in the degree of strategic complementarity. The more I care about other people's actions, the more I then care about their beliefs, the more the aggregate price level is going to reflect my beliefs about other people's actions and beliefs.
Normally when we make the assumption that rationality, there's common knowledge of rationality, that doesn't get us all the way to equilibrium. It gets us to rationalizable outcomes, but there could be a lot of those. You seem to be wanting to pin things down.
I'm not going to talk about multiple equilibria. Yeah.
Sorry?
I'm not going to talk about multiple equilibria. I'm going to just focus on.
But even if there's a unique equilibrium, there might be many rationalizable outcomes with common knowledge of rationality. So it seems you're assuming more than just common knowledge of rationality to focus on equilibrium.
Common knowledge of some kind of bound.
This is
Yeah.
probably orthogonal to your concern, but I would just
No,
point
fair.
out
Yeah.
that,
Yeah. Yeah.
common knowledge of rationality is not
Is not just enough. Yeah. No, fair enough. Yeah, I'm gonna focus just on the. Okay, good. So the weights are increasing in the degree of strategic complementarity, and now if there's dispersed information, these higher order beliefs are not going to collapse anymore. So we have to keep track of them. Okay, so let's make progress on these average expectations, higher order expectations of the fundamental ZT. And let me give you just a very simple example where suppose ZT is a normally distributed random variable. That's the fundamental that I'm trying to learn about. And suppose decision makers receive these private signals that I can justify with some basic rational intention type setup, where the signals are IID with some noise, and the variance, so these two variances are going to be, of course, important because they're going to give us the rate at which the decision maker is learning about the fundamental. So then I can write a decision maker's first order expectation, so the optimal estimate of ZT conditional on the signal as being just G, this gain parameter, that's the ratio of these variances, G times the signal. And then I can integrate over all the people in the economy, over all the signals, and I can get that the average first order expectation is going to be just G times ZT. Okay? And in this way I can keep going, so I can compute the second order expectation of a particular decision maker. That's going to be this decision maker's belief conditional on the signal he or she received. So this decision maker's belief about the first order average expectation. Right? That's going to be G squared times the signal. I can again integrate that to get the average second order expectation. That's going to be G squared times ZT. G is a number less than 1. Right? So signals are, there's some noise to the signals. There's not full precision. And I can keep going where the average kth order expectation about the fundamental is given by G, this gain to the K times the fundamental. Okay? So I have dampening in the extent to which higher order beliefs respond to the fundamental.
Can you show the previous slide, please? Okay, the mean was 0.
Yeah. Right, I would have some prior. Sure. Yes. Yeah. Sure. Good. Okay, so now we can put it all together and we can say that the aggregate outcome, the average price in the economy, is going to be a weighted average of these gains times the fundamental, right, with the weights given by the strategic complementarity and the gains given by the precision of the signals relative to the volatility of the fundamental. Okay. Okay, so as I mentioned, stronger strategic complementarity means that you're going to put, that the aggregate outcome is going to put higher weight on higher order beliefs, right? But higher order beliefs respond less and less to the fundamental. So stronger strategic complementarity is going to give you an aggregate outcome that puts more weight on these less responsive higher order beliefs, that is, that basically responds less to the fundamental. Okay? So this is how strategic complementarities amplify the information friction itself, right? If we didn't have the strategic complementarity, this would, kind of, the extent to which we'd have any effects, would be very limited, right? But these strategic complementarities amplify this. So here's a figure from Mike's 2003 paper, which takes this setting into a dynamic context and says, okay, let's suppose, so here I assume that ZT was just IID. Let's suppose ZT is actually persistent. And let's solve for these higher order beliefs, and let's solve for the aggregate price level. And let's suppose that the fundamental is, so the exogenous variable ZT, let's suppose that's just log nominal GDP. So that's P times Y, the price level times the level of GDP. Okay, and there's a shock to it, normalized to 1. And so nominal demand is permanently higher after the shock. What we would expect under full information would be for the price level to jump immediately, and that's it, no real effects, no responsive output, right? So here, this is showing well, this is showing just the higher order beliefs. Okay. So we would expect the price to just jump like this. Now, with imperfect information and strategic complementarity, what do we have? We have that the first order expectation, this is kind of like the partial equilibrium response. This is how much the average expectation of the fundamental moves, right? So that moves quite a bit, right? But then the higher order beliefs, how much the expectation of the expectation moves and how much the expectation of the expectation moves, move less and less and less, right? And the stronger strategic complementarity, the more weight you're going to put on these values, right? So why is that intuitively? How does this actually work in the price setting context? Well, so suppose that I actually have a really good signal, a really accurate signal, right? So we can even think about, suppose that I have actually perfect information about the fundamental. And so I could respond immediately, right? On impact, I know what P times Y is. But if I respond on impact, then my price is going to be misaligned relative to everybody else's price, right? And so even if I get the opportunity to adjust on impact, I'm not going to do it fully because that would bring me into misalignment with everybody else. On top of that, I actually also know that when they get the opportunity to adjust, they will also not want to deviate too much from the aggregate. So they will also not respond fully. So this makes me now respond even less when I have the opportunity to adjust because I know that they won't adjust as much. And then in turn, they knowing that I won't adjust will adjust even less and so on. And so that's why you get this significant dampening. Okay, good. So strategic complementarity is a key driver of sluggishness in aggregate macrodynamics in the presence of even small other frictions, right? They amplify other frictions, informational or otherwise, a lot. And so the issue, though, is that empirical studies often find only limited evidence that decision makers engage in really sophisticated strategic thinking, in really higher order reasoning, right? So in many experiments testing strategic thinking, in even kind of very simple basic environments, people typically engage in at least one round, at most, kind of 1 round or 2 rounds of reasoning about what others are doing and what others are thinking. Right? So how should we think about this in the macro context? So you are familiar with the P guessing game, right? So just as a reminder, consider the following game. A large number of people have to state simultaneously a number in this interval 0 to 100, and the winner is the person whose number is closest to P fraction of the average, where P is a number less than 1, let's say. So in the original, it's either 2/3 or a half, right? And basically, the sequence of reasoning for this game is some people might be non-strategic completely, right? I'm going to call these level 0. I will not take into account what others are doing. I'm just going to guess 50, my prior based on the 0-100 interval. Right? Level 1 people are going to do the reasoning as follows. I think that everybody else will be level 0. So they will play 50. I will best respond to that. So I will play 2/3 of 50. Right? Level 2 people think, I think that other players think that everyone will play 50. So then they will play 33. I will best respond to that, and so on, right? And so people keep iterating. And if you keep iterating, the best response, the rational expectations response is 0, right? Now, of course, in practice, in experiments, people rarely get to 0. This has been kind of extensively tested in the lab in very many different settings. And it tends to estimate a small proportion of level 0 people, right? So people don't just, randomly pick 50. There are spikes at levels 1, level 2. Medians are around level 2. And then there are some so-called worldly players in the name of Stahl and Wilson. This is to say, your payoff maximizing strategy is not rational expectations when everybody else is not doing rational expectations. So some people are quite good at figuring out the depth of reasoning of other people, and so we call those worldly people. And then, there is, something to kind of give us worry about how much we can extend this to macro type setting, is that there's some evidence that, maybe there's improvement with experience in the game, maybe there's maybe there's some correlation with cognitive ability, with the ability to reason about other things. Maybe familiarity of the people you're interacting with might affect the experimenter's estimates of how deep strategic thinking is, right? But it's a very intuitive way to introduce bounded rationality in G settings. And it's actually gotten quite a bit of interest recently in macro applications. And what's interesting is that if you take level K and you stick it into a macro model, oftentimes the policy prescriptions that you get regarding policies like should the government, if they want to stimulate the economy, should they cut taxes or increase spending, or how effective is monetary policy in terms of things like forward guidance or quantitative easing, these things tend to change in the level K. The predictions of the effectiveness of these policies tend to be different in a world where, say, consumers are level K thinkers rather than rational expectations thinkers. And they don't often change in, intuitive necessarily directions, right? So Farhi and Verning show that forward guidance is dampened when people have level K expectations, right? Because people don't, iterate on the general equilibrium outcome, to up to level infinity, so that limits the extent to which they take into account very distant outcomes of the endogenous variable. Mercati and co-authors find that taxes are much more effective when the economy is stuck at the zero lower bound than government spending multipliers. Because when you have fiscal stimulus, there's going to be kind of this trade-off between the initial wealth effect coming from the fact that you're going to have to pay higher taxes if the government is spending more, or if the government is taxing less today, they're going to have to tax in the future. So there's a negative wealth effect. But then there are also general equilibrium effects that come from the fact that the stimulus is going to affect aggregate demand, and it's going to affect your income, right? If the stimulus is successful, your future income is going to go up, but that goes through the general equilibrium. And if you have limited ability to reason about the evolution of endogenous variables, then that's going to be much more dampened than the direct wealth effect. Yeah.
You were just talking about consumers, but in your earlier discussion, you were focusing on firms.
Yes.
It's not quite clear to me how consumers are being modeled in these settings. Are they maximizing discounted sum of utility of consumption?
Yes.
So they have to be able to predict price. Just
That's
as
right.
firms want to predict prices, consumers want to predict prices as well.
That's right, and they want to predict interest rates, and they want to predict the path of aggregate outcome into the infinite future. Aggregate income.
And in
outcome.
these models, are consumers considered to be bounded in the same way that firms are? Or?
Yes. So that's the right. That's the idea. What if we introduce this bound on consumers' ability to reason about endogenous variables in these dynamic kind of settings? What does that do to how consumers respond to policies?
Right. But what about?
And we can do also on the firms, yeah, because these are GE.
I mean, it's not clear to me who are the agents who are being bounded in these studies?
Firms and consumers.
Both.
Yeah.
But at different levels, same level?
Okay, so this is a wonderful question. How do you set, okay, so number one, how do you set level 0? What is level 0, the non-strategic in this environment? And number two, what should you use for the level of strategic sophistication? And does it differ by firm? So we have no empirical guidance on this front, right? So we have a vast literature, and this is kind of the point of the experiment that I'm going to talk about in a little bit. We have a vast amount of evidence on these kind of one-shot games, right? Like the P-style guessing games. We have virtually no evidence on these kinds of dynamic models where that are so relevant for consumers and firms in general equilibrium macro models. So this is precisely why, just because you know that in one-shot games the median level is 2, let's say, and the level 0 randomizes across the possible outcomes, the feasible, choices of the other players, that doesn't mean that we could use that in these macro models, right? So what these guys do is they make very kind of sensible first pass assumptions. They say, look, we have no idea. So what we're going to do is we're going to say that we're going to define the level 0, which is essentially a free parameter. We're going to define level 0 to be the partial equilibrium response. We're going to say the level 0 people don't think about how prices are going to respond to a shock. Like let's say there's a government spending shock, right? That's going to hit you on impact. You're going to want to re-optimize, right? That's going to have equilibrium effects on market prices and outcomes. Level 0, I'm going to suppose they don't think about these equilibrium outcomes. They, for example, suppose that the equilibrium outcomes stay at the values that they had right before the shock happened, right? But you could say, well, what if they stay at the steady state value? Or what if, I don't know, right? You could have all kinds of assumptions. And then they say, what level of sophistication should we use for people? Let's use 2, let's use 3, because that's what the gains literature tells us is a reasonable number, but who knows? And then you could, in principle, estimate.
That's what I was going to
Yes.
say. You could estimate and see which level
Yes.
gives you the best fit.
Yes. That's right. Yeah. But it would be nice to have kind of independent experimental evidence on this. And so that's what I'm going to talk about next. Literally next. Okay, so in this experiment with Mel and Mike, we kind of want to have a games type experiment, but with macro-inspired deviations. So we're going to have participants repeatedly estimating the probability of drawing a green ring from a virtual box that contains green and red rings. Participants are going to be placed in groups, in small groups, admittedly, and in each group, the true probability, PT, of drawing a green ring on any given trial is going to be exactly like I showed you before, right? So this probability is going to be an exogenous fundamental ZT plus alpha, a parameter that we choose, times the aggregate forecast of the other people, of all the people in the group. Okay? And the reason this has a hat is because it's the average forecast. Okay, and we're going to say the initial Z in each session is drawn uniformly from just a small set of 3 possible values. 0.05, 15, 25. Alpha is going to be 0.7. And after each ring draw, there's a small probability, delta of 0.5%. Of an intercept shift, of a change in Z, in which case a new Z value is drawn uniformly with uniform probability from this set. Okay, so these are the possible states. So, and this is the best response function for each possible state. So we have 5, the intercept is 5%, 15%, 25%. And then whatever your belief about the average forecast is, you can read off of this what your forecast, your best response should be to that belief, right? And so we show the subjects this. We tell the subjects everything about how Z evolves, what the possible values are, the law of motion for the true probability, everything.
So you're going to collect these forecasts and then you're going to place that many rings into the box.
That's right. So let me show you what the subject sees. So this is the screen. So a lot going on here. So let's focus first on this best response graph, right? So at every point in time, they're shown the best response line as a function of the current fundamental, where I have marked the extremes. If you believe the average forecast is 0, then your best response is 15%. And if you believe the average forecast is 1, your best response is 85%. Now you see why we chose these values for Z, to make sure that, that the probability stays in 0, 1. Okay, okay, good. So you have this best response function, and then what do? How do you record your forecast as a participant? Well, you have a slider up here, and you can move the mouse up and down. Moving the mouse up and down moves this line, right? And you pick what your estimate of the probability is, and you could, right, if you're a model-based guy or gal, you can pick by reading off of this graph what your best response should be, whatever model you might have about the average forecast, right? Okay, so you click and you drag this slider bar, okay, and to make sure that we don't get stuck and the experiment doesn't take too long, you only have 3 seconds until the ring is drawn, right? So you have 3 seconds to make your forecast, and then after 3 seconds, the box is formed in the bowels of the computer, and then a ring pops out of it, right? And the box is formed according to the probability given by everybody's forecast and the fundamental, okay? So this box is going to have some P in it. A ring will appear out of the box, okay? And your cumulative payoff will be updated, right, as a function of the difference between your forecast and the realization squared. Okay? And people are explained. We explain to people their payoff as well. Okay.
So they have full information about Z.
Yes.
Right? They can read it up.
That's yes. And we actually show them this beforehand, right? So they know. Yeah. And they have They have information about delta. They have practice with this. And in fact, so it was funny. I'm not an expert in experimental design, but this was very amusing to me. So Mel was saying that initially when he ran this experiment, people were coordinating on the clicks of the slider, and so he had to give everybody headphones so that they wouldn't like think, oh, this person's moving the slider a lot. Maybe I should move the slider a lot too, or so yeah. That was pretty funny. Okay, so now you might wonder, why do we have this, right? So this, showing of the rings, if you're familiar with the other experiment with Mike and Mel, where we show people ring draws and then they have to update their forecast of an exogenous probability. That one doesn't have any strategic task, right? You might say, well, if I can see the rings, that actually gives me a pretty good model of how to tackle this task. Maybe I don't understand the model. I don't understand this best response function business. I don't like it. I don't want to use it. I can, if I want to, as a participant, just monitor the rings and watch the rings, right? This is the payoff, okay? This is the timeline I said, okay? All right, so this, yeah.
May I ask a small methodological question? So,
Yes.
am I right that every 3 seconds it's pretty much an independent route? They're not really strategically connected in any way, other than it's the same group of people?
Yes, and it's not independent because the Z is slowly moving.
Yeah, but it kind of, if I would assume that Z is just, I see it, right? It's
You see it, yes, yes.
So it's kind of, doesn't matter what Z I had in the last 3-second round,
You
because
would
now I
think.
see the current Z.
Yes,
right?
yes, yes.
But then, if they're pretty much independent, was there a strong reason to have cumulative payoffs assumptions? Because one thing that you could do is that they are paid for a random 3-second round out of all the rounds. So in experimental economics, it's supposed to have the welfare effects with the risk reference evolution over the rounds that you don't want to mess with what you're looking for. So I'm just
Sure.
wondering whether there was a strong reason to do the cumulative.
Sure. I think, the payoffs that they're getting are like $18, $20 for this experiment. So we're thinking, there's probably not very strong risk aversion effects going on at these kinds of levels. So we're kind of assuming risk neutrality for these states.
It does make the incentive more visible, because they can see what they're doing. So
Yeah,
There
that's
are
right.
arguments from both
No, I understand.
sides.
No, I
so-
understand the other argument, but I'm just saying, what is the argument?
Yeah, I'm just wondering
Clear.
if there are kind of extra arguments that I don't know from the standard methodology that are specific to this particular case.
Yeah.
In my experience, people are also a little bit risk averse also with probability points. Like they don't follow the theory of using probability points exactly.
Oh, sure. I think what we're focusing on is how the strategic element affects that.
So I think that if there's value on having the payoffs of that might overpower the theory of probability points risk aversion.
Oh, yeah. I think the focus really for us was to make it really transparent for them and to make it easy for them to see exactly what Mike was saying, right? To see how their choices are affecting their payoffs in real time, to have the opportunity to adjust if they need to, just like in real time, firms see the outcomes of their pricing decisions, consumers see the outcomes of their investment decisions. So they're kind of seeing this cumulative payoff in real time to potentially learn and improve their strategy.
So just as kind of a sanity check, you wouldn't expect anyone to be below 15 or above 85 in this round, right?
If they use this,
Yeah, if they're reading what you put for them on the screen properly.
right, if they choose to use this information.
If you think that level 0 players don't think about their best response to what other people are you're saying you don't
partially.
think people should be level 0 if they understand the structure. I'm just saying relative to the traditional literature.
Usually level 0 is interpreted as, not fully strategically or randomizing across everything, so.
Right. Which means
Zero
you're not
strategic.
You're not
Right.
thinking about the strategic considerations. So that would mean you don't look at that diagram. I mean, we make the diagram very visible, it's true. We want to make sure people have every opportunity to understand the structure of the game. But level 0 are by hypothesis, people who don't think of it.
So I'll rephrase the question. We should have a small percentage of people playing outside, because they're level 0, they're also uniformly picking across everything.
Are they though?
Well, that's usually what the assumption
That's
is.
right, that's
And
right.
then
And
the
so
other
we
thing
want to
is we
think
have only
about
a
is
small
that.
percentage of level 0 players, especially as the game moves on. So what is the percentage of people that play outside?
Well, I'm going to show you. That's right. Yeah. Very good question. This is precisely why we're designing this experiment in this way, because it's kind of tweaking a little bit the experiments that we're used to, right? And so we want to see, are we recovering the results that we're used to also? And I don't want to make any should type statements about what people should or shouldn't do. Yes?
Yeah, if the motivation of the experiment is to gather data and numbers about how much in depth people reason, wouldn't it be a problem that it's only 3 seconds that they have, while in reality they have a lot more time to think about these things?
So that's fair. I mean, so on the one hand, kind of there's the practical consideration of we don't want to keep people in the lab too long. On the other hand, there's also kind of this notion that we actually do make a lot of economic decisions pretty frequently and quickly, and we don't necessarily deliberate that much. And so how good are we at decision making kind of on a frequent, quick, basis? And on a kind of intuitive basis, right? How good are we at intuitively? Like if we give these guys this experiment, and in the extreme, give them a textbook on game theory, send them home, and ask them to come back a week later, the results are going to be very different. But
Yeah, I'm just wondering if there are differences in results if you don't give them time pressure, because time pressure affects a lot of results in many different
yes, no, that's fair. And we didn't. So did we?
The point of what going fast is not the source of time pressure. It's just the interest of the project is the dynamics. What we want to study is when there are changes in fundamentals, what happens immediately, what happens a bit later, what happens after a longer time, because that's what the macro models are interested in. Because when there's some kind of change, what's the difference between very short run effects and how persistent are those effects? And so that, we wanted to have a number of changes in fundamentals, first of all, but we also wanted to trace dynamics over time between changes in fundamentals. And so that's what can happen when it's only takes 3 seconds, is you can have many ring draws between each change in fundamentals, and you can have several changes in fundamentals occur during the session.
So if you remember, the probability that this fundamental will change is very, very small, precisely because we want to give people the opportunity to learn what the fundamental is and to kind of, either figure this out by thinking about it, right? Because it's not like you have only 3 seconds to think about this, right? You have 3 seconds on this round, but this Z is going to stick around for a while, right? So, you can think about it, or you can watch the rings and accumulate enough evidence to think about it, and then we want to see how you respond to a shift.
No,
in
I
this.
understand now. Yeah,
Yeah.
it's the dynamics are interesting.
Yeah. Because we only want to keep them for half an hour, right? Or,
What happens if I don't click within 3 seconds?
then your existing forecast is recorded, wherever the slider is.
From the previous.
Yes. And so, yes, okay, but I'll show you, I'll come back to that, because they actually move a lot on their slider. Okay, so the key changes from this kind of class of Bernoulli random variable forecasting of Gallistel and co-authors, adding a strategic component, making the exogenous fundamental public, visibly displaying it on the screen, and showing the participants both the best response function and the sequence of ring realizations. Okay, and as I mentioned, we want to have both of these two things on the screen. This allows us to test two classes of forecasting models, the model-based and the experience-based class of models. Right, so using the best response functions, participants can provide a model-based forecast depending on their belief about the aggregate forecast, however that belief might have been formed, and we can ask questions about how that belief might have been formed under the assumption that they're using the model-based forecasting rule. But alternatively, they could just use the ring realizations in an experience-based model. And we're particularly interested in these two classes of models because, first of all, they both converge to rational expectations equilibrium, right? Given enough time, enough ring realizations, people are going to learn what the fundamental is, and so they're going to get awfully close to the rational expectations best response, which is just zt over 1 minus alpha, right? You know, given enough strategic sophistication, right, as the level of reasoning grows, they converge to the rational expectations. Right? They capture important classes of models in macro, for macro dynamics, learning, adaptive learning, and level K. And also importantly, we added the intercept to the intercept shift, so the shift in the fundamental, because while they both converge to the rational expectations equilibrium, they differ sharply in the predictions that they make about how subjects should respond to an intercept shift. In the model-based version, the shift in the forecast should be immediate. The person sees that the z has shifted, and they should immediately jump to a new estimate of what the probability of the rings is based on this new value of z. Whereas in the learning model, people are not going to be paying attention to the shift at all, so they're only going to gradually learn that the intercept has shifted through the sequence of new, ring realizations drawn from a new box.
From this worldly player, and I'm still going to look at the ring realizations. That tells me, that gives me some information about what's the distribution of levels in the population at least.
Yes.
Okay.
Yes. Yes. Okay, so let me show you a little bit of descriptive results. So first of all, performance. How do these people do? So I'm showing you here across the subjects the total number of points observed in the participants, and you see some participants do not so well and other participants do really well, right? We can compare these to, speaking of worldly people, we can compare this to the rational expectation score. If I had in each session, if I had a rational expectations player, how would they do, right? So, they would do, reasonably well, but actually it's hard to see. The observed scores are often higher than the rational expectation scores. So a rational expectation individual wouldn't do necessarily very well in some of these sessions at least. And then we can also compare to the score that a participant would get if they knew the hidden probability. So why am I showing you this? Because this is giving you a sense of the difficulty of the forecasting problem. So they're making these forecasts based on the ring realizations. There's some noise in that process of the ring realization. So even if you know the hidden probability, right, your score is going to deviate. So you see, these guys here are just, it's not that they're particularly bad at this task, it's that they're facing a pretty hard forecasting problem, okay, because the ring realizations are just really noisy in this session, right? And these guys here, it's not that they're particularly sophisticated at tackling this task, is that they're facing ring realizations that are really informative, and so it's an easier forecasting problem for them, okay? On the whole, what I want to say is that, people don't do terribly relative to either the rational expectations scores or these kind of like best possible response type scores. Okay, so they're doing this task quite well, right? Okay, good. Okay, so how do they adjust? So the rational expectations model predicts that, as I said, when the exogenous state changes, all subjects should immediately adjust to the new equilibrium on impact, and there should be no further adjustment thereafter until there's another z change. Subjects are shown the intercept and the slope, so we can see if they use this information and how. So here's some examples of the data. So these are group averages. Okay, so in red, I'm showing you the rational expectations optimal forecast. And you see how it shifts. This is telling you there's been shifts in the fundamental of these points. And in blue, I'm showing you the P hat, the blue B bar hat, upper, the group average. And you see there are kind of different dynamics in different sessions. So this session does pretty well, right? So it's kind of tracking the rational expectations forecast quite well. It's noisy around it. Sometimes it's persistently below it, but it's not, it's not so bad. This group is also interesting, right? So it's it's tracking, it's at 0.5, so who knows if they're actually tracking or if they're just around 0.5, okay. But then when the fundamental shifts, they slowly pick up on it. This is the group average, right? And then when the here they pick up on it quite fast, but only partially, right? And then they slowly keep adjusting down, right? So there's a lot of persistence and kind of gradual adjustment, right? Not really suggestive of the model-based approach in this session necessarily, right? Very partial, very gradual adjustment, right? We can look at individual sessions, individual subjects, and here I can go back to the inaction, what happens if you don't move the slider. So in the previous experiment that did not have the strategic component, where people were just forecasting the exogenous fundamental, we saw long and frequent periods of inaction in which participants did not update their forecasts at all, right? So you might imagine a similar pattern in this strategic setting. If anything, there should be even more inaction in this setting, right? Because the fundamental is there on the screen, you see it, it hasn't changed, right? And in fact, actually what we see is much more volatility in individual forecasts, right? So we do not see inaction, which was quite surprising. So, for example, this particular subject has some periods of inaction, right? This guy looks, but they're very short. They're much shorter than what we saw in the non-strategic task experiment. Okay, so these guys are working really hard trying to figure out what's going on in this setting. Okay, so here we have a subject who, doesn't really, maybe very, very slowly adjust and then seems to kind of become better over time, right? So that's why it's important to have a long session, right? So this guy seems to do quite well. This guy seems to be tracking, reasonably well, noisy. This decision maker is very noisy all throughout. Okay, so this decision maker is clearly in this room right now. So this guy knows exactly what's up. So this was actually Mel asked. Mel followed up, and this was, I forget if it was a business. They're not worldly. Hence, they're in this room. That's right. So he followed up, and the person had taken a game theory class. So
He probably, or she probably did.
it was a he, but yeah. Hmm?
That person probably did worse by not trying to infer what the other.
Yes, that's right. That's right. So the non-worldly.
Was the person that would say zero in the beauty
Yes.
context.
Yes, that's right. Yeah.
What were your findings about learning? Are you going to show this?
Yeah, yeah. So what I'm showing you descriptive statistics, and then I'm going to show you some model estimates where we're going to think about different models of level. Yeah.
So now back to my question.
Yes.
Where would you put the non-rationalizable items?
The non-strategic guys?
No,
Or-
if I had to draw horizontal lines there of what really can't be rationalized if I know my best response function.
So session 6, subject 1.
He's playing way outside of those bounds, but even some of these other guys
Here.
might be jumping out of these bounds. Yeah. Of like, that's something that seems more like level 0, and then what percentage of these people have something like that?
Okay, so but you think this is level 0?
Well, I don't know, so that's the question,
I know.
because there's definitely playing 1 is never optimal, right?
It's not consistent with level 1.
It's not
or
consistent
higher.
with any form of strategic thinking.
Yeah, so I guess you would, you want a deterministic model of level K. So you don't want to allow for noise. So I want to relax that in the models that I'm going to talk about. Okay. Okay, so let's talk a little bit, before we get to the models, let's talk a little bit about the dynamics of adjustment to the intercept shift. And this is where the two models, the model-based and the learning, are going to differ significantly. So I want to consider the impulse response of the average forecast at time t plus h for some horizon, h from 0 on, in response to a change in the fundamental at time t, relative to the expected change in the forecast in the absence of such a change in the fundamental. Right? So, for example, if I have a change in the fundamental at time 0, this is going to decay, right? Because there's some probability delta that I'm going to draw a new value from the unit interval for z, right? So it's going to decay at this slow gradual rate. So the rational expectation, I've normalized here so that this is actually the rational expectations response, not the z itself. Okay? And then we can plot the participants' aggregated impulse response function, and you see it's very incomplete, very sluggish adjustment, much more so than in the non-strategic experiment. Okay, so there's something about the strategic task that is making these, even though they're adjusting much more, they're just adjusting to the fundamental much less. This is the 95% confidence interval. Okay. Where is this slow adjustment coming from? Well, it's not necessarily so much coming from lack of adjustment. So I can plot the cumulative fraction of adjusters over time. I have the log scale on the x-axis to show you early adjustment more clearly. And you see that, on impact, after a shock is the dark blue line, more than about 25%, I think, or 24% of people adjust on impact. And then gradually more and more people adjust. After 10 trials, so after 10, clicks out of 1,000, almost 80% of subjects have adjusted at least once, right? And I can compare that to a Calvo model where the probability of adjustment is constant and exogenous and doesn't depend on the state. I can think about a Calvo model that has the same average frequency of adjustment, right? And you see, there's basically no difference on impact. And if, they do adjust a little slower later on than the Calvo model predicts, right? But really, the frequency with which people adjust is not what's driving the sluggish adjustment. And this kind of is related a little bit to what I was talking about yesterday, that the timing dimension doesn't seem to be what's generating the big results. It's what people do when they adjust, whether they adjust often or not, right? And what do they do when they adjust? Well, they have forecasts that are very dispersed and biased, actually. So here I'm showing you the distribution of individual forecasts for the different states, low, mid, high. I'm showing you that distribution relative to the rational expectations forecast. And I'm giving you the mean of the subjective forecasts. And you see that there's huge dispersion, right, in the forecast. And there's also bias. So in the low state, the average forecast is systematically higher than the rational expectations forecast. In the high state, the average forecast is lower than the rational expectations bias. So these mistakes, or whatever you might want to call them, do not wash out with aggregation. And that's what's causing really sluggish partial adjustment. Yeah?
I think there's some factor of cognitive uncertainty, like judging by the first one where the distribution seems to be very centered. Maybe many people don't know what those are happening, the effects.
Many people don't know.
Like they go with a default, like a 50, with a forecast of
I mean,
5.
we should see a spike. So in the other experiment, in the non-strategic experiment, for example, we saw spikes at round numbers, even though they had to adjust using a mouse, so it didn't favor it. Here we don't see that much. Okay. So now let's talk about these models, estimated models. So I'm going to talk about a class of stochastic level K models from the start. So there's so much noise and dispersion that I'm going to introduce stochasticity from the start. Okay. And I'm going to motivate that by thinking about decision makers that form beliefs about the expected ring realizations on each trial, and they face some sort of cognitive or control frictions that introduce stochasticity in their recorded forecasts. And so I'm going to use the notation p hat it to denote the recorded forecast of individual I on trial t, and let pi it be the distribution from which this forecast is drawn, conditional on the hidden probability, right? And I can ask, what does this distribution looks like? And if the decision maker exerts no effort, then their recorded forecast would be a random value between 0 and 1 with a mean of 0.5. This default is going to be the entropy maximizing distribution in our context. And I'm going to assume that the cost of drawing a forecast from a distribution that deviates from this default, from the uniform default, is going to be proportional to the entropy reduction of that achieved by that distribution, which in the context of the uniform just means of the uniform distribution as the default is going to just boil down to a cost that's linear in the entropy of the distribution. Okay, and then I'm going to consider different models. So let MI be a decision maker's subjective model of how P is determined. We're not going to have a story of why people have these different models, right? So we're just going to say, let's posit a model and let's see how well it fits at explaining the data. Okay. And so this model MI is going to imply some particular forecast in period t. And then the optimal recorded forecast distribution, pi, I'm abusing notation here a little bit, this distribution of the forecast conditional on the model forecast, is going to have this form that you now recognize, or maybe not now, maybe you've recognized it for a long time, right? So it's a function of the of e to the value of this forecast, divided by lambda, which is this unit cost, unit entropy cost, right? That was theta yesterday, lambda now, and normalized, right? I don't have here a reference distribution. That just falls out because the reference is uniform, okay? Okay. And then this distribution is actually going to be truncated to the unit interval, okay? Now, as an alternative, so here I'm saying the decision makers themselves, the participants themselves truncate the distribution. Alternatively, I'm not going to show you results today, but alternatively, you can think of a model where the decision makers don't think about truncating the distribution, and what we're observing is censored data. And that's why we see these spikes at 0 and 1, that is just the decision maker was drawing forecasts according to this distribution. The slider didn't let them go outside the interval, and so we're seeing censored data from that distribution. Okay, and so that's the stochasticity. So now let's think about the standard level K model, right? So level 0 is going to be random, right? And so I'm going to have a level 0 forecaster draw a forecast from a truncated normal with mean 0.5 and some variance, that is the control cost, the entropy cost, over 2, so normalized. Okay? And then I can estimate how well does a level 0 model with lambda I fit. Then level 1 forecasters are going to take the average level 0 forecast and best respond to that. They're going to have their own stochastic forecast. Each level 1 individual is going to be drawing forecasts from this truncated normal with a mean that is given by their own level 1 forecast and a variance given by their own control cost. Right? And I can keep going like this, right? And then I can estimate for each decision maker these parameters, k, right? K and lambda. Okay, so here are the estimated parameters. Okay, so this doesn't look too bad, right? So we have level 0, 10% of the subjects are level 0. And they have actually a pretty low cost, at least relative to these other folks down here, the higher levels of strategic sophistication. We actually have pretty high levels of strategic sophistication, with 16 people who are estimated to be rational in this model, but but with very high control costs, right? Very high entropy costs. Okay, so here we're not allowing at all use of the rings, right? So let's think about a more sophisticated level 0 decision maker who doesn't just randomly pick forecasts, but actually uses the rings, okay? So we see in the data that forecasts tend to be serially correlated, and they also correlate with recently realized ring draws. So let's incorporate learning. The level 0 decision makers watch the rings, and let's suppose, like in a big literature in macro, that they apply a constant gain learning algorithm to form their forecast. So the level 0 forecast of a decision maker in a given period is going to be a weighted average between their previous forecast and the ring realization, where the gain parameter gamma reflects how quickly they're responding to news, right, to information about the state. Right? Now here, this becomes now my model forecast, and the realized forecast is going to be drawn from a distribution centered on this, right, and with a variance that depends on this subject's entropy cost. Now, alternatively, we can say, well, we also see a lot of serial correlation in errors in the data. We see forecasts systematically deviating for a long time from the ring realization. So maybe we want to introduce serial correlation in the errors, and instead of modeling learning relative to the previous theoretical deterministic model, we can model learning relative to the realization of the ring draw in the previous trial, so relative to p hat, right? So then that introduces any noise in p hat it is going to then propagate to t plus 1, right? So we're going to have serially correlated noise. Okay. Now these are the level 0 people, and now let's suppose the higher level people, the level 1 people and above, are sophisticated and they understand that the level 0 people are doing this ring watching. So then in order to forecast their forecast, they have to also watch the rings. They now can't just do the model based forecast and that's it. They have to do both. Okay, so they form their beliefs about the lower levels, and each level is anchored by this by their own learning model with their own gain parameter. Okay, and this, allowing for this learning, actually generates a much better fit. Yeah.
Just a clarification. So there is a cost of reducing my variance of around my mean. Is there a cost also to reasoning higher levels?
No.
Okay.
Yeah.
I mean, there might or might not be. You're not modeling.
Yeah, we're not modeling it. Yes. Yeah, we're not modeling it. Okay, so here are the estimated parameters. Okay, so what you see now is that the level of strategic sophistication declines significantly, right? So a lot of what we thought in the kind of pure standard level K model was strategic sophistication was actually just people learning by watching the ring realizations, okay? It was not people being strategic. And the proportion of level 0 non-strategic subjects jumps dramatically, right? Almost half of the people are, better characterized by a model where they don't even think about the best response function, right? They just watch the rings. These are not the same people that did the other experiments, so it's not like we're contaminating, okay? Okay, also, much more reasonable entropy costs, right? We need much less errors to rationalize the data once we allow people to learn, right? Because then they can get these patterns of deviating from the rational expectations or from the model-based forecast with much lower entropy costs. Okay, and then so there is still that one guy. Remember him, right? Okay, so it's hanging strong. Okay, so he's not learning anything. He's just modeling. Okay, and then the gain. So I mean, we don't really have a clear theory. It seems like the gain is increasing in the level of sophistication. So I'm not sure why higher levels should be more sensitive to data than lower levels. But I mean, if this is confirmed in bigger studies, that could be an interesting idea. Okay. And the gain, what's more intuitive is that the gain is positively correlated with entropy cost, right? So this, this oversensitivity to news is generating high entropy costs, which makes sense. Okay, good. So we're making progress. So learning helps a lot, at least in this task. Stochastic level K with learning. Now, the learning algorithm really improves the fit, in part because it's the only source of persistence in the forecast, and we saw that the forecasts are very persistent in the data. So let's allow for persistence in higher level forecasts independently of the persistence that comes from level 0 forecasts. Okay? And so again, drawing on inspiration from macro models, let's consider higher levels being inattentive to the value of z, right? So they might not notice right away that the intercept has shifted, right? We really don't see very few subjects actually adjust on impact, right? Whether by little or by a lot, right? Very few of them pick up on the intercept shift right away. So let's allow them to be strategic but late, okay? Good. So I'm going to have now another parameter, phi, denoting the probability that a decision maker does not notice if the fundamental value has changed at the beginning of period t. Okay, this is going to be constant, and I want to estimate this phi. The level 0 guys don't care about inattention. They're not paying attention to the fundamental anyway, and they're not paying attention to other people who might be paying attention to the fundamentals, so they're not affected. But the inattentive level 1 decision maker now, I'm going to have a whole cohort of these, not a whole cohort, a whole set of cohorts of these people, right? I'm going to index each cohort by h, right? So a decision maker in cohort h is a decision maker who last noticed the value of the fundamental h periods ago, right? And so he's going to have some belief about the fundamental, zt minus h. It's going to be the same across all decision makers with that, within that cohort. And then this decision maker is going to also form a forecast about the level 0 average forecast. The level 0 forecast doesn't depend on inattentiveness. So this is going to just be based on the usual learning. Well, not usual, usual now, right? Learning, they're going to keep watching the rings, and sometimes they're going to notice the fundamental, and sometimes not. Okay? They're going to still have stochasticity. So I have stochastic level K with learning in the level 0. And I have these different cohorts, right? Some people noticed it in H0, H equal 1, and so on. So the expected level 1 forecast across the cohorts of inattentiveness is going to be some weighted average of each cohort's forecast, where the weighted average depends on this phi parameter, okay? Good. Okay, so what's the estimation of the parameters now? So we actually, one thing that kind of was really surprising to me is that we actually killed the rational expectations guy. So we probably shouldn't have killed the rational expectations guy, right? I don't know. Okay, so, but what we see is, setting aside that guy, we see now that it's just really level 0 and level 1. So there are people who watch the rings, and there are people who watch the rings and watch the fundamental inattentively. Okay. What does this do? It generates lower entropy costs. So that's kind of good, because this, we want to explain as much of the stochasticity in forecast as we can, right? It also lowers the learning gains, right? We don't need so much sensitivity to news anymore. And further improves the fit. Okay. Okay, good. So the share of level 0 forecaster. So I'm going to wrap up a little early. The share of
one question.
Yes.
Quite a standard question. I always ask people. So why don't you ask people
why they're doing what they're doing? Yeah. I mean, so humans are very good at ex post rationalizations.
So what?
So what?
So
It's
ask
not
them
clear
ask
that
them even what is the advice that they would give to another person.
Yeah. Advice to others, yeah.
Even.
Yeah, and if there are systematic
That
patterns.
way you don't need to do any estimations.
Well, I don't know if we wouldn't have to do any estimation.
Why?
Because I
10
don't.
people will tell you this, 5 people will tell you this, 2 people will tell you something that you did not really know.
Yeah.
Maybe not 2, probably 50% probably will tell us things that we don't think.
Are they conscious about the way they're making these intuitive
Why not?
judgments? This is kind of like in the,
If they didn't take care of it, if they just click, then we will not have any explanation.
Yes.
Actually, and then it's not meaningful.
yes, yes.
So you will not, or you will have also this information about what are the proportion of people that actually did not take it seriously.
So they do take it seriously, right?
Maybe,
A lot of them,
but
yeah.
maybe not. Some,
Some, yeah.
15%.
Yeah. No, and I think it would be good. So there is some recent work in macro that has started doing this. So they've started asking consumers, not just what they think the forecast for inflation is going to be, but also why they think that, and trying to understand kind of what model of the world they have in their heads. And so I think
Here it's even more simple. There must be something.
here it's even more simple. Yeah. No, that's fair. So this is, I think this is kind of, step one in this literature. I think much more work needs to
But
be done.
usually step one is the last one.
But just a comment on this, that there is quite some evidence on implicit versus explicit learning. So people are able to do things, but they're not able to justify them. So you would lose that implicit learning people if you ask them to write in a text box. If you ask them, no, you don't lose anything, but if you only take into account that data of the text box, then you lose all the implicit learning.
I mean, I agree completely. This is related to the ex post rationalization and how valuable it is. But I also agree with Ariel that we would learn something from it, right? We might not learn everything, but there is information.
Learn more.
Yeah. That's fair. Yeah. Okay, so the share of level 0 forecasters in this experiment is much, much higher than what's usually estimated in the one-shot games. And this gap reflects the experimental design, the fact that we allow people to have these two ways of responding to the task, and also the modeling strategy, that we actually allow for models of experiential forecasting in which people don't need to rely on strategic model-based reasoning. And that significantly reduces the degree of strategic sophistication. Also, allowing for inattentiveness significantly helps fitting the data. So for contexts with repeated feedback, like in macro, where decision makers have the opportunity to observe and learn from outcomes, and where they have to monitor market conditions or the state continuously, then imposing kind of the standard level K model without augmenting it with some form of inattention and some form of learning might actually lead us to overstate the degree of strategic sophistication in the data. Yeah.
So there's all sorts of new eye tracking technology with webcams. Did you think of tracking where people, because you have a screen with a lot of information.
Yeah, that's a great idea. Yeah. So that would be nice. Yeah. So I don't have money for that, but.
Simple webcam. You can do it now with just a simple webcam.
I mean,
It's cheap. If you have it on most labs, and at least in our lab, we have webcams on the computers. And it's simple.
Okay.
And then you can see, are people looking
Yeah,
at the range?
yeah,
Are people
that's
looking
right.
at the
Yes.
response function?
That's right. So, I mean, I think you can view this as kind of like a proof of concept experiment a little bit, right? There's a lot more to be done. Absolutely. Yeah. Okay, good. So, okay, so this control lab experiment kind of, like I said, is really kind of a first step in trying to think about experiments with strategic decision making in settings that are kind of relevant to macro. And encompassing these kind of deviations from the basic level K model helps significantly predict behavior. Why is this important? Because strategic complementarity is central to propagation and amplification of frictions in macro models, and level K provides a very intuitive framework to introduce bounded rationality in these kinds of environments. But we still have a lot more to learn about how it interacts with things like imperfect information and with things like learning and inattentiveness that might be very fruitful going forward. And might inform these models of these general equilibrium models that are just kind of making assumptions